thanks everyone for attending. I want to show you something very pretty in my opinion that I discovered in the last 6 years. It's kind of a framework for modeling a lot of things, and it explains a lot of, it's a big unifying picture that explains a lot of things that I was previously confused about. So hopefully you feel the same way. So this is based on, is this working? Oh, maybe it's because I dropped it. Okay, this is based on, I'll just sit here for a second. Joint work with my advisor, Joe Halpern. Although he and I don't always see eye to eye, so I don't want to put his name on the entire presentation. He helped develop some of these ideas, but I don't think he endorses all of them. Okay, so let me just remind you what the standard picture of a rational agent, a rational decision maker looks like. And I'll do it in my own idiosyncratic notation because it'll be important later and I want you to get used to it. So you've got some set of states that you could be in, S, and you have a probability distribution P over what those states could be. So these are your beliefs. You also have some set capital A of possible actions you could take, and you want to take an action, one of those, or a distribution over those, that's little a. The whole point of an action, sometimes the definition of an action, is that given a state and an action, you get to an outcome. The double-headed arrow just means deterministic, although it's not super important. I'll just get you used to my notation. So now you have an outcome, and from an outcome, you have some utility. And if you're rational, you satisfy certain axioms, then you sort of have to behave as though you are making decisions this way. That's the standard theory.
What little p and small a stand for?
Little p is a probability distribution over S. Little a is a probability distribution over A.
Okay, cool.
In general, arrows are conditional probabilities. We'll get there in a second. But the double-headed arrows will represent the special case where there's no randomness. It's just a deterministic function. Okay, but there's some problems conceptually. Maybe one is, if this is the set of all possible states you conceive of, then do you really have to have a full distribution over S to make sense of things? Some people would argue no. Joe argued no yesterday. We're going to see a dual notion of like, what if you have too much information to have one of these things? Okay, so maybe you don't want to have your distribution, your beliefs represented this way. Another problem is, where do utilities come from? That's an even bigger problem. Are all utilities equally good? According to the standard theory, the answer is yes, and I still can't use my mouse.
Can I ask a question about that picture?
Yes.
Should I think of this agent as being uncertain which state it is in, and that's what we mean by the probability distribution over S?
Yes.
Yeah, got it. Oh,
Yes.
okay.
I feel like I've broken it. Okay, let me just sit over here. Okay, so the same problem happens in science. So this is how you write a scientific paper. You first come up with a problem, and then you solve the problem. And we love problem solving, that's why we're here, that's why we're mathematicians and computer scientists. It's what we're good at, and it's also what modern machine learning architecture, formalism is good at. Once we give it the formal problem statement, we can solve the problem. But an even more important part of this is to define the problem in the first place. It's really critical to machine learning. It involves selecting your training data, your loss. It's the task specification. But unfortunately, unlike solving the problem, like coming up with the problem doesn't have a good metric of was it a good problem. Like, how do you know? And it's clearly related to alignment because this is, in some way, alignment is what values shall we give to the AI system, what problem shall we solve? Okay, but while you can argue about what values are appropriate in many different cases, there's one thing that we can all agree on, and that is inconsistency is bad. If you're going to use a probabilistic picture, then if you have any inconsistency, you can be Dutch book. If you have inconsistent beliefs, people can humiliate you, they can make money off of you. There's centuries of philosophical and mathematical theory saying this is a bad idea. It's not just a preference like I like apples. This is something that we can defend. But it only makes sense to talk about consistency being your objective if you can sort of measure it, if you can represent inconsistency. So although we all agree that inconsistency is bad, it turns out we're going to be able to get a lot of mileage out of being able to represent it. So here's the representation that all of this work is based on. It's called a probabilistic dependency graph. We've already seen one example. And it has information at two levels. There's the qualitative level, which will be written in orange throughout, and the quantitative probabilistic level, which will be written in blue. Qualitatively, you've got some graphical structure. Technically, this is a directed hypergraph here in my presentation, but it turns out that you don't need that. You could just use a normal graph. It has to be directed, but just some combinatorial object.
So hypergraph is a graph where you can have like edges between edges, or like edges between edges and nodes?
Hypergraph is something where you can, we saw an example.
Okay.
You have two tails here. You can have your sources and your targets can be multiple nodes.
Okay.
Yeah.
How is this different than just having two arrows?
We will see that very shortly. But keep that in mind, that there is a difference, and hypergraphs are more expressive. Okay, so let's go through what I mean by conditional distribution, because there are a couple things you could mean. What I mean is not quite what Popper means. It's what machine learning people normally mean. So P of y given x is a conditional probability distribution. It means for every value of x, you get a distribution over values of y. And you draw that as something like this. That's the qualitative structural part of a way of representing something of this type. That's the directed hypergraph of P of y given x. Okay, so for example, if you had a classifier that takes in an image and gives you a label, that would be one kind of conditional probability distribution, one kind of CPD. Okay, what if I had a joint dependence? What if I had z that depended on both x and y? I'd draw it like this. An example involves what if you have both an image and audio, multiple inputs to your network, no problem. Okay, what if I had an unconditional distribution? What if I didn't want to put anything into my network? I just have P of x. Well, I'll just draw this without any tail, nothing at the tail, and still one head. It's a distribution over x that doesn't depend on anything. Priors are an example of something like this. Or a constraint. If you had a deterministic, you said one variable certainly happens, an event that you observe, that is an example of an unconditional distribution that also happens to be deterministic. And what about a joint distribution? We've seen things with two tails, but if we have two heads, that means I've given a joint distribution over two things. So this is different from two separate arrows because a distribution over z and also a distribution over y is different from a joint distribution over xy. So for example, if you had training data of pairs xy, that could be represented as an empirical joint distribution. Yeah.
So on this graph, y has like two arrows going into it, right?
Right.
Representing like two different probability distributions.
Right.
And so, am I right that the way this is different from like a Bayesian DAG or something is that like you're just drawing a whole bunch of different probability distributions, some of which are redundant?
Redundant or possibly conflicting.
Or conflicting.
Right.
Amazing. Great.
So and once you have this structure, like a Bayesian network, when you specify it by construction, it gives you one probability distribution that is consistent with everything you specified. But here, we've given two distributions over y, and a priori, they could be different distributions. So that's part of why this is more expressive than a DAG.
Okay.
Very, very astute question.
Is there a reason you're using the kind of dual notation from the usual markup category notation?
Using dual, right. The reason is because, they're equivalent, and this coincides with normal graphical models literature. So there's the circuit view and there's the string view, there's the string / circuit view, and then there's the flowchart / graphical model view. I'm using the graphical model picture. So you can, there's actually, for directed hypergraphs, there's actually a really, really nice thing where you can just swap everywhere there's a hyperarc, you can put a node there, and everywhere there's a node, you can put a hyperarc there. You can take the dual of this hypergraph. It's just like anyway, it's an equivalent representation. This is closer to the graphical model stuff.
I may have missed this, so what's the difference between just two lines and them connecting together?
Right. Dependence. joint dependence versus two independent distributions. For two arrows, one to z and one to y is a distribution over y and a distribution over z. This is a distribution over y, z jointly.
Okay.
We'll see the other version of that in a moment. Okay. So formally, a directed hypergraph is a set of nodes and a set of hyperarcs. Each hyperarc has a set of sources and a set of targets. Great. A probabilistic dependency graph, a PDG, is just a directed hypergraph where I've just annotated every node with a set of possible values, so now they're variables. And I've annotated every hyperarc with a conditional probability, and also a confidence. The confidence is unnecessary. You can just have many different copies of it if you want, but we'll just weight it by a weight of 0 means it's not even there. A weight of infinity means it's super, super important. It's just like having many, many copies of it.
But are they weighted like in addition to the conditional probabilities that
Yes, these are in addition.
Okay.
But as I said, you can do just as well without it. It's just nicer to have this in the framework because it makes PDGs a vector space. Yep.
When you say you can do just as well without it,
I mean that you can represent the same PDGs up.
I think I
Just fold the weights into CPDs.
Instead of having weight 2, you have 2 edges.
I think I don't believe that because weights could potentially be irrational numbers.
Right. So that is a good question, and I don't want to claim anything about that right now. But
Great, cool.
I can get back to you on that.
Okay.
Yeah. It'll depend on the semantics, which will be super smooth, so it won't be a problem.
Oh, okay, great.
Sorry, how should I interpret the conferences? Or is that
Oh yeah. I may as well say. Confidence. Choose your favorite reference person. Call him Bob. Bob is a little bit trustworthy, but not super trustworthy. If Bob were to tell you something, you would give it confidence 1. That's unit 1. The units don't matter. If 2 independent people who were just as trustworthy as Bob were to tell you something, you give it confidence 2. If someone were to tell you something and you know, you'd need 2 of them to tell it to you before you believed it came from Bob, then you give it confidence 1.
In this case, I annotated the y box with R.
Mm-hmm.
Is it implied that there's some sigma algebra
Yeah.
here?
Well, I'm typically not going to actually draw the set of possible variables. Yes, you need a sigma algebra to make sense of it being a probability distribution. Formally, it'll be even easier to assume that it comes with a base measure, which will carry also a sigma algebra. Okay, great. So let me be more formal about the full thing that I'm talking about. So, set of nodes, set of hyperarcs, a confidence and functional dependence along each hyperarc. This is how much you believe that the targets are really a function of the source. There's like where the causal part of this comes from. Do you really believe this is the causal picture or not? For simplicity, just think this is either 0 or 1, depending on whether that's actually a mechanism that determines things. This is a weighted directed hypergraph. Now, so this is structural information, and then you've got observational information, which parallels it. So for each set of nodes, you associate it with a measurable space, including the sigma algebra. For each conditional probability, or for each arc, you associate it with a conditional probability, and you also gave a quantitative confidence beta in how reliable that conditional probability is. And this is a functor from the free category generated by paths in this hypergraph to Markov kernels, but whatever. Okay.
Can you live out for a second? Sorry. No, I mean, I'm fine. Go ahead. I'm sorry.
Yeah.
And maybe like how is mass delta different from mass?
Measurable spaces. The Kleisli category
Oh,
or the
Kleisli.
monad delta.
Okay.
Yeah. This is. It's important that this is a nice natural object, and that's why I want to show it. I'm not going to talk too much about category P today.
Are confidences allowed to be negative?
They're allowed to be, although if this is your first time thinking about it, maybe avoid thinking about it that way.
Alright, great.
Okay, so
sorry, what's the kind of relation between alpha and beta? Well, that question.
yeah, alpha is a structural piece of information. It exists only at the level of the graph. It's like a weight on the edge itself. Beta is your it's like confidence in this functional dependence here, up to noise. Like this is the causal mechanism that's appropriate. Beta is your confidence in the reliability of this conditional probability distribution quantitative information.
Okay.
And is that functor the claim that that data of mu p beta is equivalent to a functor? Is that the claim?
I'm saying, yeah, the calligraphic V and P give the action of this functor on nodes and arcs respectively. Great. So let me just show you how this relates to the standard graphical model stuff. So if you had a Bayesian network, here's a really standard one people use to teach Bayesian networks. Whether or not your parents smoke is PS. That's a variable. Because it has no parents, it has an unconditional distribution over it, so you need an arrow like this. Both the arrows from S to being a smoker and whether or not you have secondhand smoke just look just the same as before. So if you're only looking at Markov chains and things like this, then it's really easy to mistake a PDG for a Bayesian network. In fact, a Markov chain is the same as a PDG or a Bayesian network. But what makes it really different is this joint dependence. It's not two different arrows. These two arrows are not two different mechanisms. There's one mechanism by which cancer is determined by both S and SH. And so we need a hyperarc like this. That's very different from saying, oh, first I studied smoking and I figured out how that affected cancer, and separately I studied secondhand smoke and figured out how that affected cancer. No, you have one study that determines both. That's how you translate a Bayesian network. A Bayesian network has semantics at two levels. It models not just these probability distributions, but also some independencies. So we're going to need something in the semantics to take care of both of those things. But critically, a PDG can model multiple variables with beliefs of the same variable. That was the question asked right at the beginning. So this is why it's more expressive. Like now we're going to see some things that a PDG can do that a Bayesian network cannot. So suppose that we now learn that tanning is maybe related to cancer, and we run a study where we study how tanning beds affect cancer. We can just add this to a PDG, but it's not possible to add that to a Bayesian network. You need to run a joint study where you also control for smoking and secondhand smoke in order to add this information.
So a few times I feel like you've talked about mechanisms and causes. Like, should I just think of these as conditional probabilities, or should I think of them as like having causal info in them?
Yeah, if you put alpha equals 0, then they're just conditional probabilities. If you put alpha equals 1, then you think of them as causal. I'm not gonna tomorrow morning I'll talk about causality more. Today I really want to just show you the picture of how if you only have observational information, you don't care too much about causality, all the things that fall out. So we're going to really focus on the probability part, but I needed to say something about independency so I could show you how it's a graphical model. Okay, so they're super modular. Here is my PDG where I added something. I can just delete this node, that's still a PDG. Here's another PDG, I can combine them. They're two parallel arcs, that's not a problem. You have two different distributions about how T affects C, that's no issue. It's still a PDG. But right now, one question is, what does this mean? I've just told you, you can put a bunch of probabilities in a box, and you can draw them on a piece of paper. That's basically all I've said. Now we're going to do the interesting part where we show how to interpret these as useful things. So graphical models have semantics in terms of joint distributions over all the variables. So this space will be the set of distributions over the values of all the variables x. So one thing you could imagine doing is you could take all the distributions that match the structure, the probabilities you gave. This is some set that happens to be convex, so I drew it as a square. You could also take a set of distributions that match the independencies. It's not clear what that means for a hypergraph, but that's not convex when you make it precise. So this is one thing you could do. But now if you had PDG that was inconsistent, then all distributions, every PDG that would be inconsistent, even if it's only a little bit inconsistent, would have the same semantics if we stop here. So intuitively, if you had two different distributions over a variable x that differed only by 0.001, that would have the same semantics as if they just completely said different things, and that seems problematic. And we, as we were saying, we wanted to capture inconsistency in a useful way. We wanted to admit it and not have everything fall apart. So let's go to the next level. Let's consider a scoring function over all joint probability distributions, where given a candidate distribution, it'll tell you how much you failed to match the information that you've provided. So how how much have you violated your probabilities, and how much have you violated the structural information. So this is the second kind of semantics, and this is going to be the primary thing we're going to deal with. From this, though, you can get a set of distributions that match your probabilities, the zero set, and you can also get a distribution that typically will be a unique one that represents your possibly even inconsistent information. There's one final semantics, and that's just this number. How inconsistent are you? How far is this off the plane? How far from zero? So if you take the best distribution, and it was all consistent information, then there's some distribution that matches everything, and that'll be zero inconsistency. But just this number alone, it's just the value of the inconsistency of the hypergraph, but turns out to be equivalent semantically to this full scoring function, which I think is a huge surprise.
So I think as people should call it a loss function or something like that.
Yeah.
because you want to minimize it.
So this is going to be like the universal loss function that I'm going to promise you in a second. So this number, it's just a single number. It's not a full joint distribution, but it turns out to be just as powerful semantically and algorithmically. So if you had an oracle for this, in linear time you can compute this. I'm not going to show you that result, but that'll be some other time maybe. Okay, so let me show you the scoring function. That's where we're going to start. So we have two parts. We have the hypergraph part and the probability part. And there are two kinds of entropy, fortunately. Entropy is supernatural. There are many axiomatizations of it. There are lots of good reasons to like it. I'm going to show you one more reason to like it. So there's the structural entropy. It depends only on the identities of the variables. The entropy of x, you don't really need to know anything about what values even the variable x can take in order to make sense of this quantity. It measures how much randomness is in x. We've seen this before. Your expected surprise at learning the value of x. There's also relative entropy, KL divergence, which is kind of like entropy, but it's quantitative because you get to specify your belief p. So relative entropy, it's asymmetric, and the first argument is it's sort of a natural measure of discrepancy between reality and a model. So your belief goes in the second part, and reality goes in the first part.
Are you using omega instead of x to emphasize that these are like different types or something? Different objects?
No, I didn't do that intentionally. They may as well have used omega. And so this measures how far a belief is from matching reality. It's equal to zero if and only if these two things are the same. And it has an interpretation, an information theoretic interpretation, as the excess costs of taking your beliefs seriously if in fact you're in this other distribution. Okay, so I just rewrote this so that it's compatible with measure theory. All I needed to do here was add a base measure to x. I told you that I might need that. And so technically you need a radon-Nicodemus derivative to make this all work out. And I want to just point out that it's again structural because this lambda is just, unlike mu and p, which are belief and things, you just needed this lambda, this property of the variable itself to compute the normal entropy. Okay, we've been drawing entropy in bubbles. Here's the conditional entropy, it's that crescent, and this measures how much randomness there is in y if you already know x. It's a measure of how close you are to matching functional dependence. And similarly, there's a conditional version of relative entropy. It's zero if and only if the conditional probability you've given matches the conditional marginal of the distribution mu. And they have a lot of similar properties. So you can write them like a very similar looking formula for each of them. There's an alternate way you could conceive of each of them as being actually an expectation over x. And there's an alternate way you can sort of rewrite each of them as sort of, there are a bunch of ways that you might think that the right way to define this quantity is in both cases, and fortunately because it's entropy they're all the same. So this would not be the case if you use like L2 norm to measure distance between probabilities, for instance. One more nice property of entropy, has many.
Can I ask a question on the previous slide? There was just one thing I think I missed. You generalize the notion of entropy here, I presume for the case of uncountable
I'm just reviewing normal entropy. You mean,
this
here.
generalized, is this
Yeah, yeah.
differential?
This
Is
is
differential?
differential entropy with respect to a base measure.
Okay, got it, yeah.
So the only reason this isn't relative entropy is because lambda doesn't need to be a probability measure.
Yep.
Yeah. Okay. Good. So now let me follow through and tell you what the scoring function is. Unsurprisingly, it's based on entropy. Observationally, recall that what we're trying to do. We've got a candidate distribution over joint values of x, and we want to know how incompatible is it with our beliefs. So we have this measure of discrepancy between probabilities and beliefs, and we just weight by confidence. So if you have no confidence in this belief, it doesn't really matter if you match it. If you have super high confidence, it matters a lot. Sum over edges. These things are all additive quantities. They combine independently in an additive way, so this makes a lot of sense. There's this second quantity for the structure. So intuitively, for each arc, you're saying the targets are a function of the sources. And how many bits are needed to separately so if you really believe in the causal picture along the hypergraph, you think that the sources contain up to noise all the information in the targets. So you think that the targets are mostly determined by the sources, and you're going to pay for any information that's left, weight by alpha just for the same reason, for symmetry. But you're also going to get credit for overall noise in the system. It's sort of the difference between the number of bits needed to separately determine each target from its source and the number of bits needed to determine a full sample overall. If this causal picture was correct, then these numbers would be the same, right? You could just go along your hypergraph and determine all the numbers, and that would be the same thing as just generating a sample. Yeah?
Do the alphas somehow need to add up to 1 for this to be true?
I haven't claimed anything. It is true that in order for this to be strictly positive, or non-negative, you need to have enough causal belief. So if you have no beliefs at all your alphas are 0, this is negative entropy.
Okay.
And so this results, this coincides with the normal practice of maximizing entropy subject to your observational beliefs.
Okay.
If you have causal beliefs, then this may not be the appropriate thing to do. So this actually, in some sense, solves an old problem where people weren't sure whether Bayesian networks were maximum entropy objects in some sense. And the answer is they are once you account for the entropy already specified by the probabilities. Okay, we're not going to talk about this too much though. We really want to focus on machine learning, which is all about observation and not about causality, at least to a first approximation. Alright, so to use a PDG as a probabilistic modeling tool, the optimal distributions are the ones with the best score. We'll combine them, sum these two functions together, find the distribution that's best. For the other semantics I told you about, for the inconsistency, we'll just, instead of the argument, we just calculate a minimum, it's just a number. And the one other parameter here is the relative importance of structure. How much we care about this right function, and I told you we're not going to care about it too much today, so we're going to look at this observational inconsistency where that mostly goes away. So we can take the limit as that goes to 0. Now, let me just give you a quick overview of how PDGs relate to other graphical models in sort of a map. So these two axes are the confidences alpha and beta. Alpha is scaled by gamma because it was scaled by gamma in the definition. So this is your confidence in the structure, that's your confidence in the observation. A Bayesian network is an acyclic graph where alpha is 1, so you believe everything holds causally. And because this will sort of hold, the best distribution for a Bayesian network will always be the one specified by the Bayesian network. It doesn't really matter how you choose your parameters, beta or gamma, because you can simultaneously satisfy all your independencies and every single probability distribution, so it doesn't matter what your relative weights are as long as they're positive. You'll always have the unique distribution specified by the Bayesian network. So gamma doesn't matter, it can go back and forth here in this picture. When there's enough quantitative belief, enough observational belief, there's always a unique best distribution. So that's what I meant by often there's a unique distribution specified by the PDG, and in particular there's one in the limit as gamma goes to 0, no matter what. So So you always have a unique distribution in this observational data is everything case. We don't care about structure. The extreme empiricist can always find an empirical distribution. When you tie these parameters alpha, beta together so that they're always equal to each other, and you also tie the two parts of the scoring function together by setting alpha, gamma equals 1, then you get a standard class of models called factor graphs, where you multiply everything together, you renormalize, whatever that is, that's what you meant. I think that factor graphs are uncalibrated. We'll maybe see why. But as you choose this vector alpha equals beta, that's the factored exponential family associated with the factor graph, and that's this diagonal line. For factored exponential models, the inconsistency is the free energy. So already we're seeing that this number is important because the free energy is just what happens when you view it as a factor graph and you measure its inconsistency. It's the standard number that you hope for. So to summarize, PDGs capture Bayesian networks and factor graphs. But that's just the beginning. They also capture other representations of uncertainty, which it's not so important, so crazy mathematically, but it's very, very surprising, I think, at a philosophical level. Because we started with probabilities, we added some graphical stuff, and now we have not just probability distributions, but we can also capture Dempster-Shaper belief functions. We can capture imprecise probabilities, convex sets of probabilities, which I think was surprising because we just started with probabilistic information only. You can also capture things like constraints. So here's just a quick example. Suppose we didn't know whether it was a fair coin or a biased coin, a double-headed coin. So depending on whether the bias was 0 or 1, we could have this probability distribution. If it's a double-headed coin, it's heads with probability 1. If it's a fair coin, it's 50-50. The set of distributions associated with this is the imprecise probability set associated with not knowing whether it's fair or biased. And moreover, the inconsistency of observing, as you observe more information, this sort of works like an imprecise probability. But even more so, generalizations of PDGs are themselves PDGs. So recall that we sort of used a hypergraph. We could have just as well done with a graph. So instead of writing something like this, we could have, where z depends jointly on x and y, we could have plopped in a variable xy that contains both and just written this graph with some coherence constraints. Would have been the same. We could have separated arcs into having two different kinds, where we had one that carried observational information, one that carried structural information. That would be the same. And we could have allowed conditional probabilities to be just sub-probabilities or have missing values, or instead of a probability distribution for everything, we could give a range. So all these seeming generalizations of a PDG can in fact be implemented with PDGs themselves. So if this seems strange, recall that a Turing machine, you give it extra tapes, you give it extra dimensions of tapes, you give it extra functionalities of all sorts of different kinds, and you can still run it with a Turing machine. So you don't really need to. Okay, you could also put parameters on the edges. Okay, now here's what I really want to focus on. The systems of neural networks can be captured really nicely with PDGs. So now we're back to the beginning of the talk again. We have this measure of inconsistency, and I'm going to claim that it's a universal objective, that it applies in almost every situation, and that in almost every situation it's the appropriate thing to minimize. So the way you model in this framework is you take your predictors, your models, whatever you trained, you put in your data, you put in your priors. All these things can be represented as probability distributions, possibly weighted with confidence. You just measure how inconsistent it is, and that's your loss function. So why is this better? Normally, a loss is thought of as a preference. You can't really argue with a preference. Why do you choose one loss function? It's because it seems like it'll work, or the previous paper did this, and we want to compare to it. Because that's what people in our lab do, or it's because I want what I want, and that's not a choice you can engage with or argue about. And we'd like to make principled decisions. Choice of model, on the other hand, is about reality. So beliefs can be tested, they can be validated, they can be wrong, but at least we have a way to think about how to update them. And so while we've just reduced the question of finding a loss to the question of probabilistic modeling in a nice way, that's a really important reduction, because Now we're just dealing with beliefs and we're not dealing with preferences anymore. So let me show you some examples. That's what I've focused on the rest of the time. So we have this unconditional distribution over x. We'll do the simplest possible example first. And now we learn little x, a value of x happens with probability 1. Here are two different distributions. How inconsistent is it to believe both at the same time? It's the surprisal of x, this negative log probability. So it's already the standard measure of, it's even named after a cognitive, some sort of internal conflict, the surprisal. As the standard measure of discrepancy between a probability and an event. Great, but it's totally unsurprising, given that we built this out of powerful information theoretic primitives, that we got back this very simple one. What's more interesting is that it's very, very robust. So here's this negative log likelihood. We could modify it by adding latent variables. So now we have a joint distribution, but we only observe part of it. That gives the inconsistency here is the marginal negative log likelihood, the appropriate thing in this context. You could make it a conditional model. So P is not just an unconditional distribution, it's a distribution of y given x. You give it a sample. This is the negative log, conditional log probability. We could add a data distribution, so it's not just one sample at a time, it's a full sample, a full empirical data set. And as long as we believe the data with high confidence, then this will be the cross entropy. And you can combine any combination of these and you get the right variant of entropy. So all these different axes can be combined, you get all these different kinds of entropy by measuring inconsistency.
Sorry, can you remind me the definition of the inconsistency?
Yeah. There. So the inconsistency of a PGM is just the infimum, the min, because it achieves the min over all distributions mu over joint values of x of the sum over arcs, where arcs go from sources to targets, of the relative entropy. Well, beta is the confidence in that arc. The relative entropy with respect to the distribution mu of the probability in this case. So you're looking for what's the best case conflict with all of my beliefs. So let's look at just one version of these. This is cross entropy used to train a classifier. You believe your data with very high confidence. You don't really believe your classifier so much. This is cross entropy. And the really interesting thing about this framework is that you can sort of use local adjustments of these arrows. You can break them down and you can derive inequalities and get fine structural relationships between these objects. So this empirical distribution, I can always just break it down into first the probability of x and then the probability of y given x. So you see, all I did was I factored it in the usual way. And then if I say both of these things, I say, okay, I'm going to just choose the deterministic thing. My classifier is now deterministic, and I'm going to just choose the highest probability thing from my data. That's the log accuracy. If I so that there's my high quality, my optimal predictor. If instead of taking my predictor to be deterministic, I just do exactly what I had before, but then I have it be the center of a unit normal distribution, and I take y to be a real value variable, then this is mean squared error. If you, so this is back to our cross entropy again. And if we just take our hypothesis theta at h and we say, okay, well actually we have a parameterized classifier, it's not just h on itself. Well, here's a set of parameters. I have its particular choice of parameters, little theta. This is just equivalent to what I had before with this single arc. I just pulled out parameters, chosen a particular choice, and it's the same cross entropy. And if I add a prior belief, another belief about what the parameters should have been, then I add the appropriate regularizer. So this brings out a very well-known connection in the literature between priors and regularizers. But it fits into the same framework. It all comes from the same place. So regularizers are terms added to loss functions that are just functions of the parameters to incentivize simple things. Priors are distributions over parameters. Here's one way of seeing why they coincide with each other. So in light of this, let's think about what it means to resolve inconsistencies. So here's a very, very simple setting. Our classification setting again, our parameters theta, our inputs x, and our outputs y. Let's say inputs are images and outputs are labels. So we have let's suppose it's a trained model, so we have a particular set of weights. So we have an input x prime and an output a label y. Typically this will be inconsistent. So typically when you run, you fix your architecture, you run your input image through the model with parameters theta, you get an output. It typically will not be the value y, and the degree of the inconsistency will be cross entropy. But how do you resolve it? If we resolve it by changing theta, this is just a normal training procedure for a neural network. We resolve the inconsistency here, this is learning. If we resolve the inconsistency by adjusting the label y, then this is inference. We've taken the model and the input and we've figured out the y that is consistent with it, and it's like a push forward. It's a very fancy and unnecessarily complex way of saying take the push forward of the neural network. If we resolve the inconsistency by controlling this input, then you're constructing an adversarial example. So it was, for a long time, people thought, this is just a fact of neural networks that they have adversarial examples. It's a problem with our architecture. But unless there's a really serious reason to believe there's no symmetry between your parameters and your inputs, anything that should be trainable this way should be trainable that way.
Can you specify or choose which one of these three is tweakable on the level of the structure?
On the level of the structure.
Yeah.
So structurally, I've fixed all the parameters.
Yeah.
In fact, I've set alpha equals 0, so the structural loss doesn't matter in here. I'm just talking about observations.
Yeah.
And I fixed also this graph. I'm not changing the graph. Does that answer your question?
This structure specifies the loss function.
The structure combined with the choice of model, the choice of parameter.
Yeah. Okay. Never mind. Go.
Yeah. Great. So all these standard AI problems can be viewed as different ways of resolving the same inconsistency. And inconsistency at a higher level, this was just an illustration. At a higher level, inconsistency resolution gives rise to adversarial training. I didn't show, typically when you find an adversarial perturbation, you also need like an L2 norm here. That's just like a prior from before, so you can make this all very precise and then also switch between finding adversarial examples. And if you switch between controlling these two things, that's adversarial training, which is a common defense against adversarial attacks. If you set things up right, you can get GAN training, you can get EM algorithm, even belief propagation are examples of inconsistency resolution in this way. Okay, so let me show you another class of things that inconsistencies generate. So, again, suppose we have a single variable, x, and we have two distributions over that variable, p and q. If you believe both at the same time, you're probably inconsistent, at least if p and q are different. If p and q are the same, then you have zero inconsistency, and the more different p and q are, the more inconsistency you have. So this is a measure of divergence. But there's one thing I haven't told you, and that is the confidence of p and q. Those are the four parameters that I haven't given. And it turns out you can solve this analytically. So if this is the divergence that depends on the confidence of p and q, which we're calling R and S, then you can say in closed form, this is the answer. And if this looks familiar to you, that's a good thing because many divergences can be written this way. So in this graph, the x-axis is your confidence in p, your y-axis is the confidence in q, and as you change these, you get all these standard well-known divergences. So if you're very, very confident in p, you get the relative entropy, the KL divergence, where p is reality. If you're very confident in q, you get the opposite. The Renyi divergences are a family where you fix the confidence of q equals 1 and you increase the confidence of p. But it's sort of a well-known problem that the Renyi divergences, I don't know about problem, but like weird technical quirk that you can't get reverse KL divergence, and now you can sort of see why. That point is up here, it's not on this line. To fix that, some people develop these alpha divergences which interpolate between forward and reverse KL, and that's this line. And so you can just sort of see like these Chernoff divergences are this line, the Bhattacharya is this line. You can just see all these different standard divergences. They just come, yeah.
I know there's like two big families of divergences. There's like the F divergences, and then there's like some other
Bregman.
family. Yeah, like F and Bregman.
Yeah. So these are all F divergences.
Okay.
The only divergence of both is relative entropy.
All right.
So another reason to like relative entropy. Okay. Now, again, let's use that same. Go ahead.
That is a really impressive graph.
So let's use a reasoning principle that's very intuitive. Believing more things can only make you more inconsistent. So if you had some set of beliefs before, you add some new beliefs, you can only get more conflicts. You can't possibly resolve conflicts by adopting new beliefs. That doesn't make sense. So if I take anything and I increase my confidence, I can only get higher numbers, and therefore twice the Bhattacharya distance is less than reverse KL. Therefore, the reverse KL is greater than max entropy. Therefore, Renyi divergence are monotonic in their parameter alpha. So you can just prove things about these divergences with this very simple fact. Great. So here's the data processing inequality.
Sorry, what did you prove? Just
So increasing your belief, increasing your confidences can only result in larger inconsistencies. Therefore, if I take a point, say this point here, which is twice the Bhattacharya distance, and I look at the cone of things that are larger than it, all these things must be divergence measures that are strictly larger, or maybe not strictly, that are larger. And so this point is reverse KL, and then we prove an inequality between these two things. So here's another version of this, another reasoning principle. The data processing inequality says if I started with some distribution P and Q, and I process them both in the same deterministic way, they have to get closer together as distributions. So if PDG divergences, as I guess I'd call them this way, satisfy this, it means that, before I had some divergence, after I have some divergence, after I process them both with F, they'll get closer together. Okay, let's prove this. So here's the definition of this divergence, and that's the definition of that divergence. I just used the definition I had on the previous slide. Two beliefs about the same variable. This thing on the right, I just break it into two things. I pulled out F. Here's the only thing that's at all confusing. I've added F to this PDG by adding a new variable, but because this is just the definition of Y, it doesn't add any new inconsistency. And if I take this and I split X into two parts, X1 and X2, and I enforce that they're equal, that's the same as just having one variable of X. So this equality can be enforced by having arrows going back and forth or something like this. And what's the difference between these two graphs is just that I enforced inequality.
One less constraints, so it gets slightly less inconsistent.
Right. So again, a nice visual proof of a non-trivial result. Okay, here let me do one more that's totally different. So variational autoencoders are a standard way to represent, maybe 5-10 years ago they were more popular than they are now, but they're still very much used. Suppose we have a bunch of images, we'd like to learn a compact representation of them. So our image is X, we send them through an encoder. Z, we're thinking this will be our nice compact representation, and then we would like a decoder network to decode them back into images again. So this is the setup of the architecture, and what makes it a variational autoencoder is that we also want this Z to have some nice properties. We'd like the latent codes to be maybe normally distributed, no correlation, so that they encode something useful and semantically meaningful, and we'd like Z to be smaller. So yeah, so you have some prior over Z, and you'd like to be able to sample from your prior and decode it to get a generative model. That's the idea. But how do you train it? So well, you need a loss function to train it, and it's called the elbow. There are a couple ways to get it. One is to say, well, the reconstruction error, which is the surprisal at taking a random sample from my prior, decoding it, and getting exactly back this sample I had in mind, which seems kind of like a crazy thing to do, to say, you know, how should my decoder work? I take any sample from my prior, and I decode it, and I expect to get this particular image that I have in my data set. It seems a little weird. And even weirder is you add the divergence from the prior, because you want your encoder to somehow look like your prior. But this means for every image you want it to be as close as possible to a Gaussian when you encode it, which is definitely not what you want. So this is not what you want, and that's probably not what you want, and you add them together and you get something that works. Here's another way you can justify this. It's the evidence lower bound. Arguably, you want to take your decoder, take a sample of Z, decode it, and get back your data. This is the evidence of the data. But it's too hard to do this integral, to go across your entire prior and figure out what your decoder would do. This thing is greater than that thing. You'd like to maximize your evidence. Might be sufficient to maximize this lower bound on it. But here's another lower bound, is negative infinity. It's not clear to me that this is enough to train a network. And VAEs, even though we really like to think of them as graphical models, you've got two different distributions over X. You've got the distribution over your encoder, and you've got your prior. So a typical graphical model can't really view this as a graphical model. And yeah, finally, the point is that it's not just the architecture, but also the loss function that makes a VAE work. So people have tried, like whenever you see a VAE tutorial, people talk about graphical models, and they always just leave out the encoder to solve this problem. They say, okay, here's the VAE graphical model, here it is, we have a prior encoder, we don't know what to do with that. We'd like to draw it here, but we know we can't, so we'll draw it with a dashed line or something. What if we just use a more expressive graphical model? So we had our images and our latent codes. We have an encoder. It's high confidence because the definition of the latent code is whatever the encoder gives you. We have our decoder. We have our prior. And now we learn to sample X. How inconsistent is this? It's the opposite.
Whoa.
Now, there's one free parameter, like the relative confidence of these two things. If you change this number, then you get a beta VAE, which is a class of models that are supposed to generalize these and work better by tuning these parameters. And believing more things cannot make you less inconsistent. So if we drop our encoder, then we get this, which we already saw was the evidence. This is just the cross entropy, one variant of cross entropy. So again, the inequality and the loss function, both of which were kind of opaque. To derive this inequality, you need to go through Jensen's and a bunch of algebra. Or you can just say, oh, if I drop my encoder, which is intuitively what people were doing all along, then I can't be any more inconsistent. Okay, I already did this. So, in my last couple minutes, I just want to quickly sketch another way that you can think about agency. So, typically an agent takes actions because they're trying to achieve something. They have some goal, they have some utility, but I'm going to argue that all you need is to be able to take actions to reduce your inconsistency. This doesn't make sense if you're sort of structurally never able to be inconsistent. You just have your probability distribution or whatever. You don't do anything. But now that we can represent inconsistency, we can sort of go towards the one thing we all agree that we want is consistency. So the way I'm going to, we've already seen sort of how you can do AI with minimizing inconsistency, but now I just want to show you how it generalizes the perspective that you may already have in your head. So recall, this is the standard picture of decision maker. You have actions. A, you've got states. You've got a distribution over states. Actions and states lead to outcomes. You have a utility function. Now, the only thing that's missing here, this is sort of just a probabilistic description of how these things come to be. What's missing is a way of tying good utilities to things that are more, or bad utilities to things that are more epistemic conflict. Or not, it happens to be epistemic because of the way I encode it, more conflict overall inside your mental picture. So here's, I'm gonna give you a construction which looks kind of weird, and I agree that it's kind of weird, but let me just show it to you. So let's postulate the existence of some other variable t for truth, and capital T always takes the value little t, it's always true. Not much interesting going on here. Now we're going to add a condition on the value of u. We'll say the probability of truth is proportional to x of my utility. This is some way of encoding someone who's going to throw a tantrum and say there's false things that are happening if I get bad utilities. So this is a very questionable belief. I wouldn't start here. You might distill a model and get to something like this because it sort of represents the same stuff, but it seems weird to say you're entitled to choose your preference in this way. Okay, that happens. I'm just merging these two things together, composing the two arrows. And since t is very uninteresting, it always takes the value t. I don't really want to draw the variable t anyway. I'll just get rid of it and draw this like this. So now we have beliefs, actions, and preferences in the same PEG. Typically, there will be an inconsistency, and you can resolve it in three ways. You could modify your actions, which is the standard thing, and it turns out that if you have much higher confidence in your beliefs than in your preferences, this is just utility maximization, expected utility maximization. If you have really high confidence in your preferences and you don't really take your beliefs very strongly, this is just wishful optimistic thinking, where you take whatever action would be the best in the best case scenario. If you modify your preferences, this is a different way of resolving inconsistencies. It's arguably sort of like a more zen approach to the decision problem, where you say, yes, I have a problem, but I will change what I like in this world so that it's not, the root of suffering is desire, and I will change my desires accordingly.
My advisor used to call that thinkful wishing.
Right. So if this is thinkful wishing, then wishful thinking would be modifying your beliefs, which seems like objectively a bad idea because every time you get new observations, you'll incur more and more epistemic conflict. So this is not a very viable approach to resolving the inconsistency. But that's
Wait,
what.
why aren't modifying beliefs of the Bible?
Well, I mean, you can do it temporarily, but as time goes on, you will keep incurring epistemic conflict every time you see a.
But how does that show up on the graph?
Oh well. Now you learn something else. You see some maybe as a function of state. You observe some other variable over here. You observe you get some conflict because your new observation that you had to add to your graph because your eyes told you had to will conflict with your new belief.
You can default weight to the eyes and stuff.
I would say that like it doesn't show up in the syntax of the graph, but it shows up in the semantics.
In like the way you probably use this thing.
Yes,
right?
yes, yes.
Yeah. And I'm out of time, but I will take questions.
So this is reminiscent to me of like active inference. You know, you
Yeah.
make something so hard you make it happen. Is that like? Do you think there's an important difference? And if there is, what is it?
I'm glad I'm not the only one who wanted to know.
Can you elaborate a little bit?
Active inference, it's this like theory of what brains are doing where you're just like minimizing the free energy, you just have this like joint distribution over everything, and you minimize the free energy of that distribution, which is like tail divergence something, and you do that by like having true beliefs, and you have it by acting so as to make your beliefs true, roughly.
That seems conceptually extremely closely related.
Okay, if you're not familiar, you really should be.
Yeah.
You can listen to Danny's episode with Jan Kulmaj.
So there's also notions of cognitive dissonance, of course, that are well established. I think what makes this, as far as I know, I don't know anyone else who's connected all the different parts of the puzzle, which has been there for a long time.